I made up two. I had one real one. But I did one. Yeah,
How much time do people think that people have? I don't have time to be 3 leaders, do these extracurriculars, and volunteer.
And also,
And get good grades. Like, pick one of the.
All right, here we go. So we're going to talk about the molecular structure of acids and bases and why some things are strong acids while other things are weak acids. Okay, and that comes down a lot to the structure of these molecules. So the strength of the acid, like I said, is going to determine how much it disassociates. Remember, a concentrated acid, even if it's a weak acid, can still do a lot of damage. For example, acetic acid. Okay, if you spill acetic acid, like even though it's a weak acid, it can still do a considerable amount of damage if it's highly concentrated. Hydrofluoric acid is a weak acid. That can actually, if you get it on your skin, it can actually eat away into your bone and actually destroy your bone. So it's kind of a big deal. So strong acids and bases are generally considered to disassociate completely. The stronger the acid is, the weaker its conjugate base will be. So remember, when we look at these, I forgot to turn my commenting on. You gonna work for me today or not? Come on, I just need you to work. Thank you. All right. So remember, when we're doing this, this is plus water over here. They didn't add that in, but the whole idea is that this is your acid and this is its conjugate base. So the stronger this acid is over here, the weaker this is going to be when it goes back and comes back this direction. So if this is a strong acid, this is going to be a really, really weak conjugate base. So generally speaking, the phenomenon is associated with the Ka for acids and Kb for bases of an acid that is greater than 1. So we consider anything with a K value greater than 1 to be a strong acid, or if it's a Kb value to be a strong base. When compared, that's because when compared to water, it's going to pretty much fully disassociate. So these are your strong acids. And for sulfuric, it is just the first hydrogen that comes off that is strong. The second hydrogen is going to be considered a weak acid. So for chloric acid, HClO3, it's often considered to be a strong acid, even though since its Ka is greater than 1. Okay, so it's large. It's even bigger than these. Okay. So if we're talking about weak acids or bases, they're not going to fully disassociate, and we're going to be moving back and forth between them. Binary acids then, so that's like your HCl, your HF, all of these guys, you can kind of see where their Ka values and your are down here. So your Ka values would be greater than 1 for these things. All right. And fluorine, or hydrofluoric acid, is going to be a weak acid. These are all strong acids. So HI is the strongest, HF is the weakest. In that case, the bond length and strength appears to play a major role. HI is the weakest and all the way down. So what they're talking about this playing a major role is with HF, since that hydrogen and fluorine are so close together, it becomes more difficult to pull this hydrogen away and leave the negative ion behind, as opposed to like HI, where your bond length is further, it's easier to pull that hydrogen away, thus making it a strong acid. If we're talking in terms of oxyacids, which are made up of 3 different elements, then we start to see an increase in oxygen increases the Ka value. So for example, here we've got these 3 drawn, okay? Here, this is a weak acid. This is a weak acid. This is that one a weak? Yeah, this is a strong acid and this is a strong acid. Okay, right? HClO. No, that's 4. Okay. So, as we start adding more oxygens, our Ka values are going to increase. So that's because you're going to have, remember, you've got a hydrogen that's attached here, okay? Because these are the ions. This is going to be easier or harder to pull away that hydrogen than down here, where these tend to be more electronegative. You've got all of this oxygen here, so that hydrogen is pretty easy to sneak off of there. And it ends up staying fully disassociated. Other things that affect this is the electronegativity of this particular species here. So as that electronegativity increases, then your Ka value is going to decrease, your pKa, which means your Ka increases. Okay. So carboxylic acids have these functional groups attached to them, and they end up being sometimes even double bonded on. And so it kind of stabilizes it a little bit so that it makes it a little harder to pull that hydrogen away. These should look familiar to you if you've had AP Bio.
Yes.
And why would that be?
Oh, they're what makes up DNA.
Well, most of them are.
And RNA.
Yep.
RNA.
Yep. Okay.
You're genius.
You're welcome.
Oh, it's probably because you just read.
No,
the
I
thing
knew.
that says
You read.
they're
A,
in DNA.
A goes
and
with T and C goes with G.
So these are these are bases here.
Don't say dot.
So they're going to grab on to an H here. I believe that's what happens with these. They grab on here, and then that leaves an OH behind. And so that's why they're bases. All right. If we're looking at these, we need to account for the differences here. And this fluorine right here, when we look at this, the pKa value is 2.59. This pKa value is 4.76. That means that this has a higher Ka value. Its Ka value is greater. So if I take 10 to the, -10 to the -2.59, my Ka here is 0.00257. And 476. There we go. This one is 4 times 10 to the -5. So a much higher Ka value. And they're wondering why. Well, these are acids. So that means that this hydrogen is going to come off of here, right? Because remember, acids, you're going to end up with H plus in the solution. And it's the measurement of that H plus being greater than OH minus that means that you're dealing with an acid. Here, this H is going to come off, okay? It's easier to pull this H off, and we can see that in the Ka value. It's easier for that H to come off than this H. And they're asking why. So what do you propose is different about those two?
IMFs.
No,
Mm-mm.
the strength of the acid. One's a
I
straight
understand
acid.
that. No, neither. They're both weak acids.
Oh,
The molarity.
Nope. Nope. They don't give us anything about molarity here.
The
bond.
The F.
The F, right.
Yes! Oh my God! Genius!
This is the difference. What do you know about fluorine?
Fluorine is a high electronegatividity.
Exactly. Okay. So it's going to pull on this stuff and it's going to kind of concentrate those electrons over here, making it easier to pull this hydrogen off. Does that make sense?
Yes.
All right.
Fluorine.
If we look at these, we're going to draw the structure of these. We've got our nitrogen here. We've got an oxygen coming off of here. And we've got an oxygen double bonded coming off of here. So this is our NO2, our HNO2 here. And then we would have a hydrogen attached right here. Okay. Not a pretty drawing, I'm sorry. Let me try better on this one. So I've got a nitrogen here. I've got an oxygen here. I've got another oxygen here. I've got a hydrogen bonded onto that. And then I have a double bond here with an oxygen. So this is HNO3. Now, this is a strong acid. This is a
weak.
What's the difference between these two things?
The number of oxygen.
Exactly. So the more oxygens you have, the stronger that acid is going to be. Because it's essentially going to be pulling, remember, oxygen's pretty electronegative too. Other than fluorine, it's the second most electronegative element on the periodic table. So it's by all rights quite dominating here. And the more oxygens you add, the more this is going to want to say, okay, yeah, hydrogen, bye-bye. All right, questions on that section? All right. So tonight you're doing the rest of that part.
Yes.
Now we're going to talk about pH and pKa.
Yes.
And we've already kind of previewed this a little bit. So
it should be easy.
Yeah, this shouldn't be too bad today. Okay.
Yes.
So we know that when we have a reaction, and we're giving off hydrogen ions, we can calculate a Ka value. Okay. And then if we take negative log of the Ka value, we have pKa. Okay. So negative log gives us pKa. And we know that we can rearrange this equation here. And we've seen this, I think have we talked about this year? No, we haven't. We haven't seen this year. This is getting into buffers. That's what we're going to get into with this guy.
Next.
Yep, that's coming up. So that we start that tomorrow. So this is the Henderson-Hasselbalch equation. And I actually, for buffers, I'm going to end up rearranging this guy. Okay? Because I have a simpler way. And you're like, no, you don't, Lippy. And yeah, I do. I have a simpler way of doing buffers. Just like I had a simpler way of doing, what was it? Formal charge. Okay? If you look up the way to do formal charge, like the way that most people teach it, oh, good Lord. Should minus has, baby. Should minus has. That's what you do. Okay, remember that? Okay. So this is the idea behind the Henderson-Hasselbalch equation, though. If you have pH and you have pKa, you can figure out a ratio here of your weak acid to your conjugate base. The weak acid solution then will be equal to the pKa of the acid when the HA is equal to the A minus. So if that ratio is 1, then this is going to equal this. So if you've got the same amount concentration-wise here and here, these will equal each other. Okay? So that's all they're saying there. So if the pH is less than the pKa, so if this is smaller than this guy, then we know that this ratio has to be less than 1, and vice versa. So we can look at our acid-base indicators, and we kind of touched on this a little bit yesterday or a couple of days ago, where we can look at our acid-base indicators and be able to figure out what we're going to use on these. So when you're doing this section and you have to pick out an acid-base indicator, you may need to call this up on your Chromebook so that you can see this graphic in color, because I wasn't going to print colored copies. Sorry, I'm cheap. So this is that graphic. So if, for example, you wanted, you had an endpoint where your pH was, 4, this might be a good indicator to select. So you take your Ka value, you find your pKa, and do plus or minus 1, and that indicator should have a transition point that's somewhere in between there. So, like I said, when you're deciding on an indicator, you want to make sure that the color change is completed in the steepest portion of the titration. So here, you could use any acid-base indicator that's going to change in the steepest part. So here it would be 7, because this is a strong acid, strong base. You'd want to find an indicator that changes there. So this bromothymol blue would be good. So that would probably be the best thing to select for that guy. For here, this is the steepest part. This is around 10. So you'd want to find something in that range. So this thymophthalene would probably be a good one. So you get the idea there? Okay. All right. So the indicator reaction can be shown here. So you have your indicator, which is typically a weak acid, and then you have its conjugate base. So what's going to happen is that when you're working with these, you're going to, like I said, if it's a plus or minus 1 is what you're going to want to know. And they've kind of shown you the math here, but just know the plus or minus 1 that kind of holds true for that. Okay, so I do. This red S is an acid-base indicator that changes from red to yellow. And indicators then are, when it changes, it's going to be protonated, which means that it gains a hydrogen, or deprotonated when it loses a hydrogen. So would the protonated or the deprotonated form be red? So we need to find this guy. So Alzerian red. Oh, well, we can just do this right here. It says right here, the red is at a pH of 4. So this is going to be the one with the hydrogen on it, because it has the lower pH. So the red is going to be the protonated form. You see how I figured that out?
Whichever has a lower pH.
Mm-hmm. Yep. So would this indicator be most effective for a titration of sodium hydroxide and acetic acid? So this is a strong base. This is a weak acid. Where is the equivalence point going to be for these?
7.
No.
Higher than 7.
Higher than 7. So it's going to be greater than 7.
It is 8. No.
So if this is greater than 7, what color is it going to be?
It is going to be blue.
Blue is not an option. It's red and it's yellow.
Yellow.
Yellow. Is it ever going to be red in this area?
No.
No. So this would be an ineffective. This would not be an effective indicator to use for this. Okay. All right. So here we have a pKa of nitronous acid. It's 3.16. Buffer solution is made by mixing an acid with this nitrate. When bromofoley something blue is added to the mixture, a blue color is observed. Which species is present in a greater amount, the protonated or the deprotonated?
Deprotonated.
So let's look at this guy. Bromo pKa is this. Bromofoley blue. Let's find him on our graph up here. Right here. So he's right here. So he goes from 3 to about 4.5. So 3 is yellow. And 4.5, we're going to be in solid blue. Okay. So when this guy is added to the mixture, blue color is observed. So is that going to have the hydrogen with it or without it?
With it.
I heard both.
Without.
Why?
Because it doesn't have the hydrogen on it.
Right. At this here where it's blue, pH is greater, which means that you have the deprotonated version. The yellow side is going to have the hydrogen with it. Okay? And that's all I'm doing today.
Yes!
You have homework. Your homework is 8.6 and 8.7.